The following is a conversation with Thomas van Riet, associate professor at KU Leuven, a theoretical physicist doing research in string theory and theories of supergravity. Our conversation of today is centered around string theory. I hope you will enjoy this conversation, and this is Back to the Stone Age. Thomas, what are general relativity and quantum mechanics, and which are the problems, the inconsistencies between these two theories, and what is difficult in trying to reconcile these two theories?
Yeah, these are many questions, so let me try. General relativity, I would say, is a theory which, first of all, kind of unifies space and time into a concept we call space-time. So Einstein taught us we should think of space and time as sort of space-time, the concept of space-time itself. And then it's a theory that explains how this space-time is dynamical to some extent. So there's always this naive picture that if you have matter or energy, then it curves space-time. And as it curves space-time, the way objects move in that space-time, they're sensitive to the curvature. And that is how we perceive gravity, right? So if I would throw a piece, I don't know, a pen up in the air, it goes like this. Then according to Einstein's theory of gravity, the object has followed like some kind of a shortest path in space-time. And the fact that it goes up and down is because space-time is very curved along the time direction. And effectively, you can calculate this means that you get like a parabola, right? So it's an extension of Newton's theory of gravity, which I think that's probably most important. And so we tend to say that therefore, since it's a theory of gravity, it holds on large length scales. Okay, by large, I mean large, say, compared to the size of an atom. All right. So what is quantum mechanics? Quantum mechanics is also an extension or a revision of Newton's theory of mechanics, not specifically gravity. And it's about how to think of fundamental objects, like what we call elementary particles. And quantum mechanics tells us that instead of thinking of point-like objects, as what Newton thought, or the Greeks thought, elementary objects are like almost point-like objects. It tells us that this is not really the right picture. Instead, we have more probability distributions for an object. And the object itself doesn't need to be a point. It's more, we think more of particles, say, as waves. And when these waves form like a little wave packet, so think of a sheet, right? Like the surface of water. And if I tap on the water, I can create waves. But I can always create waves in such a way that it's a bit difficult on water, but I could try to do it, where I get a blob of water going up and it's kind of localized and it could travel. Then it looks a little bit like a point-like object from far away. So quantum mechanics teaches us that the way to think of particles is like a wave, which is a little bit concentrated and can move around. And most important is that this wave, when the wave is big, right, you should think of it as a high probability to find the object which you consider to be a point particle, which it isn't. So the wave itself, the thing that's waving, is the probability distribution itself. So it's quite abstract. Yeah. Then the question is, of course, you were asking about combining relativity and quantum mechanics and why that is difficult. That's a very long story. I'm not sure what is the best angle to approach it. Okay, very naively speaking, you could say quantum mechanics describes these probability distributions over space and time, okay? But then relativity is telling us that space and time itself is dynamic. So that's how you already see a little bit the issue, right? You describe a probability over something that by itself should be described by a probability. What it is more, I would say, I mean, this is one way of saying it, but I guess the problem of combining GR, relativity, and quantum mechanics has different difficulties associated to it. And what I just told you is one. And another one, and it could be that they're related, is what is called, on technical terms, that the theory is non-renormalizable, okay? And non-renormalizability is not something specific to gravity, okay? So what is renormalizability or non-renormalizability? It is the following, that if I have a theory, which I think of as kind of a fundamental theory, right? Say electromagnetism, or what we call chromodynamics, what describes a strong nuclear force in nature, right? I can have different theories. We call them field theories, because in electromagnetic fields, right? So we think of fields, we make them quantum mechanical, we call that field theories. And when you think of a field theory as being truly fundamental, it means that you should be able to do calculations on the smallest length scales, right? Okay. Now, it turns out that sometimes when you try to do calculations at the smallest length scales, you find infinities. And I don't think these infinities are anything deep. They're just telling you that you should not trust your theories to the smallest length scales. Let me give an example that I think most people that listen to this podcast might know. It's not a perfect analogy, but I think it works well enough. If you've ever seen, like what is an electric field and what is the electric field associated to, say, a point particle that is charged, like an electron, then you find that the energy goes like a negative power of the distance. Okay, so if I go towards the electron, I would get infinitely strong electric fields and associated with an infinite large energy, which we know is impossible. It just tells us that you have to not use a classical description of electromagnetism if you get close enough to the electron, right? So this is typical in physics, that if you ask questions about two small length scales, you need a more fundamental description, right? In the case of the electron, it tells us we need quantum mechanics. It resolves that issue. But even if you have a quantum mechanical theory, sometimes when you have a quantum mechanical theory of fields and particles, it turns out that there's still like seemingly inconsistencies, right? Then there is a procedure to kind of, people say, get rid of infinities. I don't like this word, but I'm afraid I have to use it. And that means that you say, there's like a precise mathematical description where you say, okay, I think my theory is not fundamental. And so I introduce what we call a cutoff. And a cutoff is a certain distance. You could say, maybe I have a cutoff at 1 centimeter. That means I can do calculations in my theory up to a precision of 1 centimeter. And that cutoff length is throughout all of your calculations you see it appear, okay? So we call a theory renormalizable if we can set this cutoff length to 0. And we don't see any problem. And it means that our theory can describe all small length scales, right? And then there's a technical thing. You take a field theory, like relativity is actually a field theory, and then you check, is it renormalizable or not? You find it's not. Oh my God, I have this cutoff length, okay? And what does it mean also on a more practical term is that let me emphasize this. It's wrong to say that you cannot combine quantum mechanics and relativity in any trivial way. You can, on the condition you introduce this cutoff length. But when you introduce this cutoff length, the theory does not easily make predictions at small length scales. That's the issue, right? That's it. And then so when you want to have a theory of quantum gravity, which can really probe the smallest length scales, which sometimes is necessary, say you want to understand, oh, was there something like a Big Bang? if there was something like a Big Bang, the universe must have been smaller than, say, your cutoff length, right? So then you need a theory of quantum gravity that's normalizable, right? And so that's, I would say, normalizability. And the first thing I said, these are, like, roughly speaking, the two main issues of combining quantum gravity and relativity. But when we all say it's difficult, I would say no, we achieved it, right? And I think the discussion that's currently held is whether, okay, if somebody finds a theory of quantum gravity, do we know it's actually the fundamental theory that describes our universe? And to do that, you need to be able to do measurements beyond this cutoff, which we originally had. But it's very difficult to do measurements at such small length scales. We need particle accelerators that are huge. So to summarize, you often read humanity has a hard time, combining GR and quantum mechanics. I would say, yeah, it was tough, but we did it. There are concrete proposals and they genuinely achieve it. We know the mathematical difficulties that we know how to resolve them. The question is, do we know that these are the theories currently describing our universe? And for that, we need experiments at super high energies. And some of us hope that maybe we do not need to do these experiments at super high energies, right? So that's sort of I would say the difficulty with quantum gravity is exactly there. Do we need experiments at the highest energy scales? If so, we're a bit in trouble. Or are there remnants of this quantum gravity theory at energy scales and length scales that can be probed with current technology?
Okay, so we have general relativity and quantum mechanics, and one of the proposals to reconcile these two theories is indeed string theory.
Yeah.
Can you explain what is string theory and how does it emerged? How did it emerge, and how does it propose to solve this reconciliation problem?
Okay. Yeah. So when you say what is string theory, we have an understanding of string theory in certain limits. So to fully tell you what is string theory is not possible. And this is often considered a weakness. It's not. It's literally the case with every single theory we know. All right. Quantum chromodynamics, which is very good at describing the nuclear force. The way it's formulated is incomplete. And this is actually, well, I'm not going to go to the technical details, but this is essentially true for any theory we have. This is not a problem of the theory. It's a problem of humanity not having developed enough mathematics yet.
When you say
incomplete, so what you can do in physics, sorry.
Sorry, yeah. I was asking, when you say incomplete, what do you mean for a theory?
Good. So what you can do with the theory is this is a bit too technical, so I'll just drop the word and then I'll try to move away from it. You can have what we call a perturbative definition. Okay, so you write down an equation that is supposed to define the theory in a certain limit. So string theory has a clean, super precise definition, which is mathematically very well understood when the interaction between strings is small. Okay? What is nice about theory is that once you define it in a certain limit, we know mathematically it has to exist in the other limit that you're not able to describe. It will do so, it will exist in a unique way. It doesn't mean that you know how to do the calculation to describe the theory there. But it's like a little bit like, I don't know, maybe in mathematics, you know a function, you have certain properties of the function, you say, oh, it's analytic, whatever, and then you know it in a certain region. That's actually usually enough to understand the whole function everywhere, but it doesn't mean that you can actually do it. Okay? So we can prove that the theory must be unique, and we know it is there, but we only have a full understanding in the limits of the theory. And the great thing with string theory is that we understand it in many different limits, but we don't have a full understanding of it. But I think progress is going well, but it could take a long time. But I think we understand it enough in many corners to understand to already answer many questions, which is kind of nice. Yeah. And so you're asking how does string theory resolve the issue? Well, so first of all, string theory, the word says it, it means that in where we have defined the theory, where we have the full definition, it tells us that elementary particles, which in quantum mechanics are described by waves, you should not think of them as point-like objects that became waves. You should think of them as strings, literally one-dimensional objects that are vibrating. Okay, and so it's not that, well, so when you look at a one-dimensional object that is vibrating, and so what can such a one-dimensional object do? It's like a piece of wire, and it goes like this, right? It has a certain length, or it can be closed. First of all, it can propagate. It can just move around from here to there, right? And it's just like a particle moving around. But there's only one string. So how can you ever describe all particles? Well, it just turns out that the way it vibrates, if it vibrates in a different tone, it looks like a different particle. In that sense, it's very much a theory that is what we call, what we like in physics, that unifies things. Like the fundamental equation that I just told you that describes a vibrating string, that's an equation that's this big. What to me is insane and what has convinced me from the very first moment I ever learned it. So you look at the quantum mechanics of such a vibrating string, and then you just push the calculation, you ask, okay, what does this imply? And what is, to me, completely crazy is that it gives you the Einstein equations. So, I mean, you haven't asked, for instance, you haven't asked for space-time even in this description. It tells you there is something called space-time. And that space-time has to obey Einstein equations. You didn't ask for it, it came out. What's even more insane is that if you look at the four forces in nature, so we have gravity, described by Einstein equations, and then we have electromagnetism, we have the strong nuclear force, and we have the weak nuclear force. Okay, these are three non-gravitational forces. Their mathematical description is called Yang-Mills theory. Okay. And there are many Yang-Mills theories, but they all have exactly the same mathematical structure, specific equation where you can change some variables, but it's a very specific equation. Also, that equation just rolls out of string theory without asking for it. All right. So that is kind of crazy. So what is different from other approaches of quantum gravity is that they say, oh, I have the Einstein equations, which are a classical description of dynamical spacetime. And now I will make this quantum mechanical. This is not what string theory did. In fact, string theorists were not looking to describe gravity at all. Originally, they wanted to understand the nuclear force. They thought of like, I don't know, like mesons, like quarks, antiquarks, whatever, being, you know, they are confined because they're connected by a tube. And then they wanted to describe the vibrations of this tube, which turns out to be a string. And that thing started to behave like gravity. And then people suddenly realize, oh, my God, this can actually describe gravity, right? And then you're asking, how, maybe more on technical terms, how can I intuitively see that? I think it's intuitively difficult to see why string theory gives us a good theory of quantum gravity, but I would say fundamentally because we didn't put it in. It literally predicts gravity. And that I think is extremely fundamental. But on a technical level, I think the picture that I like to convey, which is not sufficiently conveyed, is the following. So I told you in the beginning that theories which are non-renormalizable, they do not have big predictive power, right? So it means that there is a length scale, and beyond, at smaller length scales, you do not know how the theory behaves. Or you do not have the theory, you just don't have it, okay? And so when you quantize gravity, you make it quantum mechanical in an ordinary way, it's non-renormalizable. But in physics, we have had non-renormalizable theories in the past, all right? And a fundamental thing we learned is that whenever we have a non-renormalizable theory, it means it's not fundamental. And it means that there, in fact, there are more degrees of freedom, more particles, so to speak. And if you would know about the existence of those particles, you would take them into account, you suddenly find that the theory becomes renormalized. This happened to the weak nuclear force, where people didn't know about what we call the W and the Z boson. And before we had a theory, which was called Fermi's four interaction theory, whatever, it was non-normalizable. It was working, but it didn't work on smallest distance scales. Then we said, hey, this was Weinberg and others. What if there's other bosons? You redo your calculation and you find a normalizable theory. And indeed, we found those particles in the experiment, right? So the bottom message, which we have learned from physics in like decades, is that whenever a theory is non-renormalizable, it means we're missing information. We're missing degrees of freedom. So then the hope is, okay, if quantum gravity has to be renormalizable, there must be new degrees of freedom. And the way string theory gives us them is that it gives us infinite amount of degrees of freedom. Namely, a string can vibrate in infinitely many ways. But for every higher tone, the particle has a huge energy. So you don't observe them. But it's this whole tower of highly energetic particles and an infinite amount of them. This is when you have a particle. So there's only one string, so there's only one trivial degree of freedom, which is super cool. But if you want to introduce that, think of it in terms of particles, there's infinitely many massive particles. And that whole tower is what you need to make gravity renormalizable. It's maybe a bit abstract. Some people like to explain it that, you get infinities in field theory because 2 points need to perfectly find each other in order to have an interaction, while a string has a sort of an extended is an extended object, so you don't have these infinities. But I think that's a bad analogy, especially to the layman, because I just told you that particles are really waves, so they're also extended, so it doesn't work too well. Yeah.
Okay.
So yeah, I know this was a bit technical, maybe it was a bit too difficult, but yeah.
Okay. The description of gravity, you said emerged naturally from string theory. And
Yeah.
I would like to ask you, how does string theory addresses the problems of singularities, as in the Big Bang, or black holes?
It's not an easy question. So it doesn't have a single answer for a very simple reason that it's not that we know the answer each time. Okay, so let me address this properly. So when we say the word singularity of space-time, what we mean is that the classical theory of gravity, so Einstein's equations, tells us that at some point, space-time becomes singular. Okay, there's like an infinite curvature of space-time. If you find that abstract, the best way to think about it is like the Big Bang singularity. All the matter in the universe was literally, if you believe the classical equations of Einstein, was compressed to a point if I wind back time. Okay? This is nothing deep about Einstein's theory. It happens in every single physics theory we have. Think of Newton's theory of gravity. The gravitational force goes like 1 over radius squared. So if I have a point particle that is gravitating, if I go towards a point particle, it's infinite strong gravitational field. Same for an electric field, right? So, and that just tells you that the theory is incomplete, which in the case of Einstein or Newton and Maxwell theory just means that you should not think of particles as genuine points. That's the answer to that problem, okay? Particles are not points. It doesn't mean they're strings, but it's quantum mechanics tells you they're spread out of objects, okay? So that kind of tames that infinity. So what you do is you have a solution to Einstein's equation, which has singularities. Typically, it means it's bullshit. It's an unphysical solution. And you do not need to use quantum gravity or something, okay? It has nothing to do with that, right? I can also find unphysical solutions of theories that are not gravitational. So, but then you have to decide if a theory has a singularity, a classical theory. Could it be that in the full quantum theory, I think it's a physical singularity, that just means that in the full theory, the quantum gravity theory, there's no singularity, okay? And so we fully achieved in string theory in the following sense. There are the cases where we know how to calculate with string theory, those limits. We find that the classical theory has a singularity. We do the calculation in string theory, there's nothing singular. But string theory does this in multiple ways. What I can do is I can give 2 ways, but there are many ways in which you can see that string theory resolves the singularity, all right? One of my favorite ones is the following. So this was done by Veneziano, Brandenberger, Waff, and many other people. Let me find the easiest way to describe a universe that has a big bang or a big crunch, okay? Where all of space-time is coming to a point, or looks like it's coming to a point. And so let me do that in mathematically the easiest way, so that I can do the calculation. And that just means that I take all the spatial directions of the universe to be circles. You could say that's weird. Is that the case with the universe today? Actually, it could. We don't know. The universe today could be that if you travel all the time to the left, you at some point appear to the right. It's perfectly consistent with how we know cosmology. Okay? The reason is that we cannot look so far in the universe because at some point everything gets dark. Right? So the universe is just so big that these could very well be big circles. There's nothing against this. So okay, let me assume the universe is a bunch of circles. Every direction is a circle. And now I wind back time. So I make these circles shrink, right? They get smaller, they get smaller. And then the way, of course, at some point they vanish. And that's what we call a singularity, right? So what string theory tells us is that this doesn't happen. It cannot happen. So if you do the calculation, what you have at first when a circle is big enough, you have strings which are effectively particles. When you look far away, they're just traveling around the circle, right? They're just moving around. But as the circle gets small, at some point it gets as small as the size of a string. It is energetically very easy to make strings winding around that circle. So, okay, that's an important thing. So suddenly when a circle gets small, the extra degrees of freedom in string theory, namely instead of a particle, you really have a little object that is, that has an extension. It can suddenly wind around the circle. And in fact, the smaller the circle becomes, the less energy it takes to wrap these strings around that circle. It's a little bit like if I give you an elastic band, it costs you energy to make it bigger. So if I ask you to wind it around something, if that something becomes very small, it becomes very easy for you to wind it around. Okay? So what is string theory? If you do the calculation, what do you see is that the fundamental degrees of freedom that an observer can observe in such a universe will be winding strings. And what is very crazy is that the theory of these winding strings becomes identical to a theory of, again, strings that are just seem to be moving. So that's very abstract. It's a calculation you can do, but what the bottom line is the following. The effective description of space-time that is of string theory, which is called T-duality, is that if the spatial direction of a universe, which is a circle, if it becomes smaller than what we call the string length, then effectively the universe opens up again. Okay? And okay. You could say, wow, that's very abstract, sure, but it's a precise mathematical computation you can do. And the physics behind it is not really quantum. You can kind of visualize it very easily. It's just that winding strings become very light. And then the theory that describes these winding strings is identical to a theory of particles where these dimensions grow again. Okay, so you see that the extra degree of freedom is winding strings. Now, there's another example, the second one, where a singularity gets resolved, which is even completely classical, but it uses an ingredient of string theory, which I think is much easier to visualize, all right? And so that is when extra dimensions of space and time come into play. So it's often said that string theory describes extra dimensions of space and time, fine, but this could also be in ordinary GR, right? In relativity, somehow by hand, we would say universe has 3 spatial dimensions and 1 time dimension. Why? Because we think that's what we observe. But then again, there could be dimensions smaller. If they're small enough, actually, they could be much bigger than an atom. We could still not see them. So, okay. So I don't think it's something fundamental to string theory, but let me use it as an ingredient that string theory actually tends to predict more than 3 spatial dimensions. So what I want to tell you is now an example of where just the classical physics of an extra dimension can resolve a singularity, right? And one example of that is I take a black hole and I take a black hole, like a solution to classical equations of Einstein, of a theory that is actually 5-dimensional gravity, but where one dimension is very small. So that an observer that is bigger than this dimension doesn't see that dimension. Okay? And in that theory, I look at Einstein's equations and I find a black hole. It's called the Kaluza-Klein black hole. It has an. And that black hole, as you famously know, black holes are singular, right? They're singular to the 4D observer. So now what you can do is you can ask yourself, how does that solution look like if I look at 5-dimensional space-time? And so what you see, and this is just a classical calculation, is that where you think there is a black hole singularity from the point of view of the 4-dimensional observer, there's nothing singular in the full 5-dimensional space-time. And that sounds abstract because it's in fact a classical computation. There's no, the only ingredients you use are the classical physics of extra dimensions, but there's like a picture you can draw to visualize this. So the picture is often called the cigar. So what do you have with a cigar? It's like a cylinder, and then that cylinder pinches off. But it pinches off kind of smoothly, right? Now think of this cylinder direction to be an extra dimension, right? So to a person that ignores this extra direction, it's like, yeah, you think that this extra direction is actually, it's pinching off, it's completely singular because one direction shrinks. Actually, it's not. It's just that, it's like space-time that is curved a bit like this, right? It's not that there is a direction completely getting, becoming singular. No, it's actually completely smooth geometry. But a 4-dimensional observer really observes this as a singularity. But a 5-dimensional observer doesn't observe this as a singularity.
Okay.
And so that kind of singularity resolution in string theory is all around, right? To me, that's clearly a healthy sign of the theory that indeed you think there's something singular, you actually sit down, you do the calculation, there's nothing singular. Yeah.
Okay. So according to one of these solution to singularities, could it be that string theory predicts or it could come out from string theory a big crunch in the past, which terminated in the Big Bang, which was the beginning of another big expansion, which is our universe?
We don't, yeah, it could be. So this scenario is called the aperiodic scenario, right? So forget about string theory, quantum gravity. When cosmologists try to understand, how did the early universe look like, and they want to use language that is not using quantum gravity, so 4-dimensional language of particles and fields and whatnot, then there are two proposals that can explain or have the power to explain the early universe and what we observe as the remnant of the early universe, which is called the cosmic microwave background. And the cosmic microwave background has certain properties. And the most important property of it is that if you look in all directions, it's a background which is very homogeneous. You could say, what's the problem? There's no problem with that. So it's like we observe photons from the early universe, okay, at a very low temperature. So it's like a radio signal throughout the sky. But we know that if you look at one direction, we look at, say, the opposite direction, according to the classical equations of Einstein, they have never been in causal contact. So they were never able to communicate with each other. So how can they look exactly the same? They don't know of each other, right? And this is called the horizon problem. And there are two ways to solve that horizon problem. Either you say the early universe went through a period where, it was a small compact thing, and then suddenly expanded super fast. And when it expands faster than the speed of light, which is actually completely fine, it doesn't violate any principle, then two things which we thought were not in contact actually were in contact before. This is called the inflationary scenario. The inflationary scenario doesn't tell us what happened before inflation. So it doesn't have the power to resolve what we call Big Bang or initial singularity problem. Okay. The other scenario is kind of the very opposite. Instead of a very rapid expansion of the universe, we believe that before, in the early universe, actually before there was the universe was bigger, it started contracting very, very slowly, actually very slowly. And then at some point it bounced and it gave rise to the universe as we know it today. Because it was contracting very slowly, before what we would think is the Big Bang, which is where the universe starts expanding again, all the parts in the sky had the chance to kind of communicate with each other, right? So that's the second way to resolve the horizon problem. And if you could describe what happens in that bounce, like when the size of the universe had a minimal size and then goes further, that bounce, cosmologists cannot describe using a non-quantum gravity theory. So yes, string theory, you could say, oh, can this scenario, ecperiodic scenario, be realized in string theory? If so, string theory should be able to calculate exactly what happens at that bounce, which is what cosmologists cannot calculate. And there are some proposals, but it remains a bit hand-waving. And the same for inflation. And that's just a technical problem. It's a problem of humanity, not of the theory. And what is a technical problem? Whenever you look at backgrounds in string theory, which are time-dependent, like in cosmology, where the universe moves, you break a symmetry of a theory. In this case, what you call the symmetry of that, there's a time isometry. And then computationally becomes very hard to do a calculation with string theory. Again, it's not a problem of string theory. It's a problem of us physicists that we need symmetries to do calculations. And I'm sure you tell it to a high school student, they all remember that when they had to do little physics problems in high school or at university, you always make assumptions which are completely unrealistic. This is the joke about spherical chickens or spherical cows, whatever they use, right? So it's the same for any theory. We need to make a lot of assumptions so we can do calculations. And one of them tends to be assuming that the theory is like the background is static. And so, yeah. So the answer to your question is maybe string theory can describe the ecperiodic scenario as a scenario for the early universe. There are some attempts, but I cannot tell you whether it will work or it will not work. Yeah.
Plus, you mentioned the string theory predicts extra dimension. How does this emergence of extra dimension from this string theory came about? And what is the nature of this extra dimension? And eventually, how can we test if we ever want to test for these extra dimensions?
Very good. I'm afraid this is probably the hardest question to explain in non-technical terms, but I'll make an effort. I think it is wrong to say that string theory requires extra dimensions of space. What it does is something else, which in some corners, limits of the theory can be interpreted as extra dimensions of space. So that's a technical remark, which I think is very important. So what happens when you want to quantum mechanically describe a string, because that's what string theory is about, okay? So you say, okay, you have the most naive picture. You say, if I have a string vibrating, it's vibrating in something, And that something is a space, there's a time, and then there will be spatial directions. And then you can write that quantum mechanical theory down. Now, when you write it down, you see that once you mathematically make it abstract, you do not need to assume anymore that there's such a thing called space and time. And for me, that's hard to explain. It's just that you have a formula, and once you have the formula, you see that immediately you can generalize it, and you do not have to give certain mathematical objects, you do not necessarily have to give them interpretation as space and time. Okay? And I think that's awesome. because it shows what many people expected way before string theory, that a fundamental theory of quantum gravity should tell us something about space-time, that it's much more abstract than we think it is. Okay, and string theory does exactly that. So string theory, mathematically, it's called a conformal field theory. And only in certain limits of that conformal field theory do you have the interpretation of space-time. And then you ask me, Thomas, what is it beyond? I cannot answer you. But what is super cool is that I can do calculations and tell you what you would observe. Okay, so that's weird. The theory is so abstract that you can actually, that we lack the human language to talk about it, but it's fine. Because in the end, what a physicist does is to do computations to say, okay, if I do this and this, what would I observe, right? Okay, good. But what I can do is I can insist on having my typical notion of space and time. So I go to that corner of string theory. And then indeed, I find that a theory where we understand the theory best, it tends to need 10 dimensions or 9 dimensions of space and 1 dimension of time. If you then want to know what is the mathematical reason for this, it's very abstract. I don't know whether it means anything to people that listen to this. It goes a bit as follows. You have a theory of a vibrating string. You want to write down its quantum mechanical equations of motion. To do that consistently, it has to have a symmetry. The symmetry can be broken by quantum effects. But you say, I don't want that. And if I don't want the symmetry to be broken, it fixes the dimension of the theory. That's how it mathematically happens. And I believe that's great. It's exact, and because you see, if I have a fundamental theory, it has to also tell me how many dimensions of space-time there are. More conservative approaches to gravity, they say, oh, we observe this, so we put it into the theory. String theory doesn't do it. You say, whatever we observe, I don't care. Let's see what the theory tells us. And then people, I think, which have sort of a bad agenda, they say, oh, yeah, okay, fine. It's cool that you guys did this, but string theory does make the wrong prediction. We don't see 9 dimensions of space. Sorry, your theory is falsified. That's utter bullshit, right? And I think this is one of the biggest misconceptions. And I've been trying to explain this in many places. I can easily cook up a theory of, say, 10-dimensional relativity. And then the majority, there can be many vacuum solutions of that theory, which are ground states, and vibrations around this ground state would describe the universe, where this theory indeed also has many small dimensions so that an observer would not observe it, right? And I think that's good. So, yeah. So then you were wondering, how can I test this? And that's the issue. And it's not just an issue of string theory, it's by definition an issue of any possible theory out there that claims to quantize gravity. Okay? So let me go back for that to the beginning of this interview. I had to explain what was the difficulty of merging gravity and quantum mechanics. And I mentioned the word non-normalizability. And if you remember, that meant that there's a length scale, a length, beyond which, if a theory is non-normalizable, I cannot do predictions. My theory is not able to calculate. Yeah, good. If you do this for gravity, the naive way, then it's what we call the Planck length. It's a very small length. It's by far the smallest length scale that we have in nature. Like the accelerator at CERN will not be there in the coming 10,000 years to even reach that small length scale. So it's out of the question that whether we can probe that length scale. But so what is important about that length scale is that naively, you would say that any theory of quantum gravity will make clear predictions at that length scale. That's true for any theory of quantum gravity. That's, if you could probe that, you would immediately see quantum gravity in your face. You could just see what is a theory of quantum gravity, right? Good. You can be lucky and you have a quantum theory of gravity that actually predicts at the scale at which things start looking quantum gravitational, is actually much larger. And with string theory, you can be lucky with this. In some cases where you have a certain background of string theory, you calculate, you find that quantum gravity effects are way, way bigger. Okay. But in general, the reason I'm emphasizing this is whether people talk about loop quantum gravity, you name it, this will always be typically physics, like general physics principles predict that you should go all the way to the Planck scale, and then for sure you will see quantum gravity effects. Good. So how do we go about? All right. So either we are lucky and string theory predicts effects already at reachable energy scales, or no. And this is a problem. So the question whether it does or not depends not on the theory. It depends on the vacuum of the theory. And maybe that is a very abstract notion, but it's absolutely crucial. So if I have a physics theory, then how can you describe the universe? Well, what you do is you go to the lowest ground, to what we call a ground state of the theory, because everything in nature goes to lowest energies, right? I mean, you're used to, you throw a ball, and then a ball will, go in, like you're playing soccer in your garden. Your garden is some kind of a non-trivial, valleys and hills. It will go into the ball will essentially go into the valleys, right? Okay, and then the way physics works is that you have a theory, it goes to its ground state, and then you have little fluctuations in the ground state. And these little fluctuations, they appear as particles and interactions, and this actually makes up the universe. So you first have you have a theory, it can be a unique theory, but it can actually have many vacua. And then you need to figure out in which of the vacua are we living. And that is the problem we have with string theory. And honestly, and there's a big misconception, it's the same problem with general relativity. It's just that it also has many vacua. It's a problem of many theories, all right? I'm not sure it should be a problem. Anyhow, it's just a feature that fundamental theories tend to have many vacua. So to answer your question, I would need to know what vacuum are we living. Since I don't know, what you could do is you can be agnostic and you say, okay, I'm just going to do measurements. But then that's a tricky game because, are we going to ask the taxpayer to pay so much money for a new accelerator, but we don't know at what length scales it will give us new effects, right? So that is a fundamental issue. Now, you can be lucky, and this is a program I work on, is that there are effects which come from the smallest length scales, which nonetheless sort of make it all the way through to the largest length scales. And that's what we're hoping for. This could happen. It's a non-obvious thing, but sometimes it can happen. There are instances where physics at the smallest energy scale somehow is able to move all the way up to reachable energy scales. But it's a difficult problem, yeah.
Okay. The problem of finding which vacuum state we live in, is it, correct me if I'm wrong, the so-called landscape problem?
It's a landscape problem, yeah.
Okay.
Yeah.
What are the so-called swampland conjectures which help us in understanding in which landscape we live in?
So I'm not sure the swampland conjectures can help tell us exactly which vacuum we live in. It does something else. Okay. So string theory has been criticized because it has a landscape. And it then sort of made it through, I don't know, popular science articles and books. There's this belief, oh, if a theory has a landscape, it has no predictive power. Because, yeah, maybe the theory is unique, but if there are many vacua, then the way the theory looks in that vacuum, it's like it can describe infinitely many theories. And that is just plain wrong. Okay. So it's very unfortunate that these wrong statements made it in popular science and became completely mainstream now. And I think the Swampland program, it's a scientific program, it's not an outreach program. But my hope is that when it goes into the outreach program, people understand how wrong this picture is. All right, so first of all, before I address it, let me say that people who don't do string theory, they have some other proposal, also have a problem of a landscape, and in fact, a way worse problem. Because what they do is that they take a theory, and then they make it quantum mechanical. They take a classical theory, and they make it quantum mechanical. There are infinitely many classical theories. Okay, so they have a way worse landscape. String theories, no. They just say vibrating string, and we'll see what happens from there. And that's a single theory. Okay. Good. So what is the Swampland program about? It is in the following. So if I take a string theory, or actually any theory of quantum gravity, imagine there's something beyond string theory, it would also apply there. And I go to a vacuum state. And I look at fluctuations around the vacuum. Then this theory will appear what we know will look like at large distances. This theory will look like what we call a field theory. Like the standard model of physics is a field theory. So it will look like classical gravity, Einstein gravity, coupled to a theory of fields and particles. Okay? The fundamental theory might be unique, but you look at large, like fluctuations in a vacuum, you then coarse grain, meaning that you look at larger length scales, and then it appears like the theories which we know. Depending on which vacuum you are, you get a different field theory. So that means that you get a theory of the electron with a certain mass, with a certain charge, and so on. And depending on which vacuum you are, these numbers will be different. That means a different field theory. Is that making sense a bit?
Yeah.
Yeah. Okay, so some people believe that, if you have a landscape, and especially landscapes as big as string theory, you can just have any field theory. If that would be true, there would be no predictive power, and this is just plain wrong. Okay? What I really love about string theory is that when you see what kind of field theories can I get off string theory, they come with very specific patterns. And that is cool, because if there are patterns, it could give string theory some predictive power, or any other theory of quantum gravity. And let me tell you a pattern which you could say, okay, I learned nothing from this, but I would strongly disagree. So one of these Swampland conjectures, which I think we should stop calling a conjecture, is essentially, I would say it's fully proven, is called the regravity conjecture. It is telling us that if I take a quantum gravity theory and I go to large length scales where it behaves like a field theory, then that field theory will be such that gravity will always be the weakest force. And you know this. So the fact that I can lift my phone from my desk is only because gravity is the weakest force, right? So the whole Earth is pulling on my phone, and my arm is strong enough to lift the phone. The forces in my arm, in the end, are electromagnetic forces. And they're way stronger than the whole Earth. Okay? To put it in other words, and an equivalent statement of this is the following. Take two electrons. They're fundamental particles, right? They have the same charge, so they electromagnetically repel each other, right? You know this. But we also know that they gravitationally attract each other. Nobody thinks about the gravitational attraction between two electrons. You only think about the electromagnetic repulsion. Why? Because gravity is so ridiculously much weaker. Okay, so of course we know this, and people say, yeah, well, I don't learn anything. But what string theory tells us is that it can never be the other way around. There can never be a universe, ever, where gravity would be stronger than, say, electromagnetism. Okay, so you could say in that sense, it's just one example of a low energy phenomenon, which comes from a theory of the highest energy scales or the smallest distance scale. And the hope with Swampland conjectures is that we will see other patterns which are more predicted. Okay. But of course, it's a program we're working on, and I think it's super exciting. It's probably the most exciting thing happening at the moment. But it's not yet clear to me whether it will for sure come with falsifiable predictions in the coming years. Yeah.
Okay. Can I ask you, what are the differences between the landscape and the swampland?
Right. So the reason it's called the Swampland program So the word landscape is the following. I told you, you have a fundamental theory like a quantum gravity theory. You can have different vacua. You go to a vacuum, you look at fluctuations in the vacuum, and then it appears like what we call a field theory. And for every vacuum, you will get another field theory. And for every quantum gravity theory with a different vacuum, you get another field theory. So the question becomes, what are the possible field theories? Right? I mean, we know the standard model of particle physics. It means gravity, classical gravity, coupled to electromagnetic force, nuclear force, the weak and the strong, with very specific numbers. Certain masses for the quarks, certain charges, certain number of flavors, blah, 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 all of these ingredients, right? If I change charges, masses, number of flavors, number of colors, I always get different field theories. So in that sense, there's an infinite landscape. Forget string theory, there's an infinite landscape of field theories I can write down. So in that sense, physics is not predictive. What we have done in physics so far is that we've made experiments and we fix parameters in that landscape of field theories. Like that's what we do at CERN, we measure. It fixes parameters, and then we hope that once we fix those parameters, we get predictive power for the remaining theory. But still, we like to do more. We like to understand why are there so many, colors, flavors, masses, what are the charges, and so on. So this is the question of what are the possible field theories that are consistent. That's different from the question, what is the field theory that describes nature? No, you want to say, what are all the possible ones? And of course, nature will be realized by one of them. And so the field theories that are plausible, in the sense that they can come all the way down, they can come from quantum gravity, we call them landscape theories, or we call them in the landscape. And a field theory that is not possible, in the sense that it cannot come from quantum gravity, is called in the swampland. So let me give an example of a theory that's in the swampland. I would take the standard model, and I would just change a number. I would change, say, the charge of the electron, or the strength of the electromagnetic field, such that an electron would gravitationally stronger interact and electromagnetic be repulsive. It's a small change in the standard model, just changing a number. We know that that's impossible. Such a theory cannot be realized by quantum gravity. Is that and we call that a swampland theory. Yeah.
Okay. How many of these theories are there out there?
You mean consistently? Like, what is this? What is like? So think of a theory space as an abstract. Okay, make a picture. There's like an x-axis, sorry, an horizontal axis and a vertical axis. So that gives me a two-dimensional plane. And dots in that plane would represent theories. Then with the way we think of is that landscape theories would be like blobs, like islands of consistent theories. And then outside of these islands would be swampland theories, forbidden theories. But how big landscape, the set of possible field theories is, we don't know. We literally have no clue. Yeah. But this is what the swampland program is about. So yeah, people try to solve that issue, hopefully. Yeah.
Okay. You mentioned about changing the strength of the electromagnetic force in the standard model. So in the standard model, which is our so far most effective theory of the physical world, we have quite some parameters describing the constant of natures.
Yeah.
I would like to ask you, how does, which is a big problem in current modern physics, how does a string theory handle the fine-tuning of the universe? Do these concepts of nature arise in string theory, or do we need to artificially plug them into the theory?
Right. So it goes back to. So the answer is essentially, if I remove the word fine-tuning from what you just asked me, it goes back what I just explained, right? So string theory is a unique theory to some extent. So there are no numbers that you put into the theory, right? You don't. You just see, you calculate what comes out. It just that the theory has many vacua. So many possible things can come out depending on where I am, which vacuum I have. So that comes back to the swampland question. What are the possible field theories that I can have and what not, right? And as I said, the swampland is all about finding patterns, finding borders, forbidden regions. So to answer, like, what is possible? That's a question. Like, that's the ultimate answer. That's the ultimate question of the swampland program. So we don't know the answer, but I gave you one example. We know that a certain number could not have been bigger than another one, based on quantum gravity, not on other principles, right? Like the strength of the gravitational interaction had to be big enough. And there's no other explanation for design quantum gravity. Yeah. So, but then you come to the issue of fine-tuning, right? I mean, that's a novel theme. And I would say the swampland has something to say about it, very non-trivial, absolutely. We already see glimpses of that, which I think is awesome. So what is fine-tuning? Fine-tuning means that certain numbers seem to be extremely weird in the standard model. Like probably the most famous one is the value of the vacuum energy in the standard model. Well, now I should say the standard model of physics and cosmology. So I can add a number to the standard model, like an overall number to what we call the Hamiltonian or the Lagrangian. It's more abstract, but it would describe the vacuum energy in the universe. And what does it do? If the vacuum energy is positive, as it looks like we observe now, it means that gravity at a very high distance, large distance, becomes repulsive. And indeed, we see that the universe, when you look at galaxies that are far away from each other, they tend to move away very fast from each other, as if there's a repulsive force pushing them away. And that's what vacuum energy does. Now, this vacuum energy is ridiculously small. And what do we mean by small? Of course, you have to, like, when you say small in physics, you always have to say small with compared to what? My phone is large compared to an atom, by small compared to the size of the Earth, right? Good. So there are principles in physics where you say to call something remarkably small or big, there's a principle that tells you with what do you have to compare it to. Okay, and the vacuum energy, apparently you have to compare to what we call this Planck scale. You remember the Planck scale I told you was this tiny length scale at which you would see quantum gravity effects. And turns out that vacuum energy is ridiculously small in those units. And it's a good thing. Because if it would be any bigger, and I'm talking about, some people say, I don't like it, but I will use it nonetheless, that if you would express this number, it's 0, comma, and then there's 120 zeros, actually 122, and then there's a non-zero digit. Imagine you would change it with 2 digits, like you would have 120 zeros and then a non-zero digit. The world could not exist. Why? The vacuum energy would be, that's already too big. Things would be pushed away so fast that galaxies could never have formed. Okay? So it appears that, okay, this is a very, very fine-tuned. And it's just fine-tuned in such a way that life is possible. So now there are two attitudes. Either you say, well, we have many vacua in string theory with many possible numbers, and it just happens to be what it is. We happen to live in that vacuum state, and in that vacuum state, there can be structure, galaxies, planets, and so life, intelligent life, that when it looks at the universe, says, wow, numbers are so small. Whereas in all these other vacua, there's no life to be formed, so nobody can say, oh, wow, it's so big, right? So that is one attitude. Another attitude is that, no, this number had to be this small, right? And so the jury is out on what answer it is. But let me give an analogy which I like a lot for making possible mistakes about fine-tuning. And here is one. So Kepler and other people, when they understood a bit the laws of how planets go around the sun, they realized that the Earth is actually in a nice spot. Because if it would have been a bit further away from the sun, we would freeze to death. And if it would be a bit closer, we would boil to death, right? And so Kepler already wanted to understand, like, oh, where is the distance Earth-Sun? Where does it come from? And he put himself the task to calculate the distance from first principles. We now think this is a joke. It was ridiculously stupid to do. The thing Kepler didn't have was Newton's laws of mechanics. And what you learn in Newton's laws of mechanics is that, oh, the way things move, like if I throw my phone up in the air, I can calculate how it moves on the condition that I tell you what is the initial position and initial velocity. The moment it leaves my hand, that's enough to calculate it, right? So it's initial conditions that determine the motion. The Earth has a distance to the sun, which is related to the initial conditions of the cloud of matter and dust that formed the early solar system. It was condensing, it created planets, and it just gave planets in those positions. So there's nothing fundamental about that number. It was about the initial form of the cloud that formed the solar system. It's what you could call a vacuum state. We look at the universe, we see infinite amount of vacuum states, right? We see many other stars which have planets around them. And typically these planets are in bad positions to not allow for life, right? So the apparent fine-tuning is not there. You just happen to live on one of these planets on which life was possible. But there's so many planets out there where life is not possible. You see? Now, there are glimpses in the Swampland program sort of that tells us, well, numbers are not arbitrary. You cannot just have any vacuum state. And so maybe, but we're not there yet. Like we could say, oh, the size of vacuum energy maybe is, for instance, related to the mass of the neutrino. And if that is true, you can actually explain vacuum energy. But this is very speculative. This is not, none of that, is sort of confirmed or people agree upon. But we're working on it. So I would say that to summarize it, we have seen clear glimpses where fine-tuning can be explained in the sense that the value of a certain number has to be related to the value of another number. Yeah. But this is, state of the art, and it's very tough. Yeah.
Okay. Is string theory a theory of everything?
I would say so, but it depends on what you mean with the word everything. It has upset people. Whenever you want to describe collective phenomena, this means, okay, let me give a simple example. I take a bucket of sand and I flip it around. Okay, what do I get? I get a pile of sand on the ground. If I give you the detailed interactions of the interactions between grains of sand, will you be able to calculate the pilots on the ground? I doubt it, right? Because it's just so many grains of sand that are involved, right? So this is why in physics and in all of science, we have developed what we call emergent theories, right? So what we know is that we flip the bucket, we typically get a shape which we can roughly calculate, but this shape is not so dependent on the details of the microscopic theory that describes the grains of sand. It doesn't work like that, right? The laws of thermodynamics are correct regardless of the details of the interactions between the elementary particles. I mean, it's not a theory of everything in the sense that the theory of psychology, it will never rely on string theory, if string theory is a theory of everything. In principle, it could, but in principle means nothing. It just means that if you have an infinitely strong computer, I could calculate, I give the computer the initial conditions of my body in this room right now and how it's moving. If I have an infinitely strong computer, it could calculate for me when I would leave my office and roughly where I will go to with a certain probability. Nobody will ever have such a computer, right? So I would say string theory shows to be has exactly all the properties to be what I call a fundamental theory of the fundamental interactions. And what I personally want of a fundamental theory is that it doesn't come with numbers that you need to put in by hand, and that it shows that we have to really, that at the smallest energy scales, distance scales, you have to rethink notions of space and time. And it has to be such that it's not you who is going to rethink it. It's a theory that tells you. As I said, we almost describe the human, we don't have the human language to tell you, like out of these equations of string theory, how to think of space-time sometimes, right? We have these non-geometric notions of space-time, and we can only throw mathematical words at it, right? And that's what I love from a fundamental theory. It should challenge us. We shouldn't challenge it. It should be challenging us, and it's exactly what it's doing. So even if it's not the right theory, if you can somehow show it doesn't describe nature, I think it's still super interesting as a model of how quantum gravity could work. Yeah.
Okay. Will a Nobel Prize be assigned for string theory during the 21st century?
I don't think so.
Why not?
Unless, because of what I said, despite that I want to be optimistic, even on the optimistic side of the Swampland program, that there's still observable signatures of quantum gravity at measurable energy scales. I think a lot of that is based on wishful thinking, but one has to be optimistic. So a Nobel Prize in string theory as a direct, or any theory of quantum gravity, by the way, if people really believe they're alternatives, none of them, I think, will get a Nobel Prize for the sake of quantum gravity. Simply because I have not yet seen compelling evidence that there will be measurable effects of quantum gravity. But, and this is also where string theory differs from other sorts, what people call competitors, is that it has given us mathematical frameworks to understand things we couldn't understand before. Right? So one of them is what is called holography. So what I can do, and I think that could get a Nobel Prize. So I could take string theory in a vacuum that I know does not describe our universe. You could say, who cares? Oh, but it's super cool, right? So one such a vacuum is called ADS5 plus S5. What is that? It describes a 5-dimensional, well, it describes a 10-dimensional universe in which 5 dimensions are compact spatial dimensions are like a sphere, and other 5 dimensions are negatively curved in what we call an anti-de Sitter space. And anti-de Sitter space is like our universe, but then with the opposite sign of the curve of the vacuum energy. So it would more describe like a contracting universe. Okay. Now, the thing is, with that universe, we can do very concrete calculations. We can understand string theory almost completely. And what have we learned? We have learned that string theory in that universe can be described fully, and now is important, by a 4-dimensional quantum field theory, which looks very much like quantum chromodynamics. It's called Yang-Mills theory. And what is very amazing is that exactly where humanity struggles to understand Yang-Mills theory, like for instance, a famous example is to mathematically precisely describe quark confinement is impossible at the moment. If you can do it, you will get a Nobel Prize and whatever mathematical prize. What string theory shows is that exactly in that region where we cannot compute like quark confinement, this string theory picture can compute it for you completely. And so now you should ask, oh, but why haven't you gotten, or string theorists haven't gotten then the Nobel Prize for describing quantum chromodynamics? Well, it's because the details of the Yang-Mills series are not exactly like quantum chromodynamics. It's more general. But it has shown us that there's a completely different way of thinking about Yang-Mills theories and mathematically describing them. Now, Yang-Mills theories describe all of the fundamental interactions of the forces. And string theory has given us a completely new tool to calculate with those theories. Similarly, it can now do so for theories of condensed matter physics. So what I think is very likely to happen is that these techniques where you describe certain regions of field theories using string theories, and then you can compute things that people were not able to compute before, things which relate to experiments which can be done, because that's what's important for a Nobel Prize. You should be able to do an experiment that confirms it. That I'm pretty sure string theory will get a Nobel Prize in the coming decades. I don't doubt it. Yeah.
Okay. Is there a string theorist or any physicist that has ever lived that you would like to collaborate on?
Yeah, of course. But I mean, they're all the heroes in the field, right? So it would be great to collaborate. But then again, when you collaborate with somebody who's exceptionally smart, it's also difficult for you because you want to contribute as well, right? So yeah.
Who would it be for string theory?
Many people, I would say. Well, Juan Malacena is I think one of the most exceptional people in our field. Actually, I had the luck to be able to collaborate for one paper with Kunron Vafa, which was amazing already. But yeah, I mean, there are many people. Yeah, but to name one person extra, it would be Juan Malacena, I would say. Yeah.
Okay.
Yeah.
What is instead the most beautiful concept in physics?
In all of physics.
All of physics.
To name a single one is difficult, I would say. Maybe I can only give one. Well, I can give many. So I don't have a particular one at the moment sticking out. But I want to give one example, which is a bit complementary to what I said. So I work on fundamental interactions. And I think one of the amazing things that we learn in physics is how the macroscopic world connects to the microscopic world without knowing the details of the microscopic world. So maybe in that sense, what I would say is Boltzmann, the formula for entropy. So entropy existed as a concept for engineers. During the industrial revolution, they wanted to understand steam engines and so on. So it was something that was just very practical, and then they had the thermodynamic laws of physics, which was very much describing things at certain length scales. It was totally irrelevant that like a gas existed out of tiny particles. Okay, and then Boltzmann was the one who connected this to the fundamental to the world of the small, and his formula of entropy relates, which is on his grave tomb famously, tells us that this practical notion of entropy, which even engineers were using, relates to exactly like entropy as a measure of the possible microscopic configurations, like positions and velocities of particles, that would give rise to, like, say, okay, I take a gas in a room, and people with a thermodynamic mind will want to know what is the pressure, what is the volume, what is the temperature, okay, or entropy, and these kind of derived concepts. Then Boltzmann came and he completely linked it to the world of the smallest. He said, oh, entropy, which is fundamental in all of that, is nothing about all the possible, like you do accounting. How many ways can I distribute particles in a room so that it gives a gas of that temperature, pressure, and so on? That turns out to be entropy. That insight, which happened a few hundred years ago, which connects the small world with the large world of emergent phenomena, I think it's amazing. It's what, like statistical physics in that sense, it's what allows us to understand the world. Like this plastic bottle contains trillions of atoms. I might know, like, if I would know the interactions between the atoms, it's still impossible for me to put it on a computer. Yet physics knows how to deal with it because of statistical behavior. And I think that's, to me, is maybe one of the most beautiful things. Yeah.
How surprising do you find that time is linked to the second law of thermodynamics?
Yeah. Yeah. That's something very deep, which I don't have a strong opinion on. So if you probe me on that, there's nothing smart I can say.
Okay. Well, is mathematics to you a tool that we merely use to describe our universe, or is the universe fundamentally mathematical in nature?
I, the problem I have with these philosophical questions is they become very linguistic. So whenever when people ask me and I try to think, what do they really mean? I'm not even sure I understand the meaning of the question because it's too intertwined with language, in my opinion. What I can say is that to me, the universe is fundamentally completely logical. Okay. My philosophical point of view is extremely lazy. I'm what they call a materialist. There's nothing but the material world for me, and the material world obeys fundamental laws, which can be described using mathematics. But doesn't mean that it's mathematics that's already invented. It could be that you need to invent new mathematics. Most likely you have to invent new mathematics. So mathematics, if maybe that's what you mean, mathematics to me is something that's fundamental. It's to be discovered. It's something that is out there and we can discover it. I'm not sure it's answering your question.
It is.
Uh,
It is. It's
it is.
a sort of a rephrasing of the question: is mathematics invented or discovered? You can give it a different interpretation, but yeah.
Probably it's both, but it's invented because in the end, well, it's discovered, but the way you discover it still uses language, which in the end comes from us being human beings. Although if we ever find an alien society, which maybe could be completely different from the way we are, mathematics will be the way to communicate with them. Because mathematics is a way for us to be able to go away from us human beings the most. Everything we do in life, every kind of science, every kind of activity, very strongly uses human language and intuition. And I think mathematics is what is able to make us move away from it because it is so abstract. And that's why I think in that sense, it's to some extent, large extent, it's discovered. It exists out of us, independent of us being humans. But probably the way we write down mathematical laws, that's where humanity comes in, and where to some extent you invent it is because you use, in the end, language which relates to us. But I don't think it's that strong. Like we use symbols that you can write on a piece of paper. An alien society will not do that. Nonetheless, we will see how they do it, and how we will be able to communicate with them. And they will find, like, they will have probably seen, like, they understand what prime numbers are. I'm pretty sure. They probably will have seen something like the Goldbach conjecture for prime numbers. I'm pretty sure you can communicate these things with them. Yeah.
Thank you for this conversation, Thomas.
It was my pleasure.
This was a conversation with Thomas van Ritta. I hope you have enjoyed this conversation. Thanks for listening, and thanks for being with us. This was Back to the Stone Age.